Thank you. Hello, everyone. Yeah, I'm a rock musician. And 15 years ago today, maybe not today, but I needed to make a website for my band. And I learned HTML and CSS. I loved it, and here we are in web development. So for the last almost 6 years, I've been working at Mapbox. And Mapbox creates a next-generation platform for interactive maps and location data. And what's cool about Mapbox is that almost everything we do is open source. And I'm also known in the mapping community for creating this very simple, very tiny library called Leaflet, which took the world by storm. And you can now see it everywhere on the internet. If you see some interactive map on a website, there's a very high chance that it's Leaflet, like, for example, on this screenshot of Facebook. But for the last 6 years, I've been working on a very different kind of beast. It's vector rendering technology, where browser pulls in raw data from the server and then renders millions of points, thousands of shapes and labels on the map in real time. And this is a much, much more difficult project that's really huge in scope. It's very complicated, and it uses WebGL, a bunch of worker threads to process data, and dozens of very sophisticated algorithms for creating this interactive mapping experience. So over the years, I became obsessed with performance, because there are lots of performance challenges in this kind of project. And since this is open source, I had the opportunity to come up with a very unique approach to my work. Within this huge complex project, which is called Mapbox.gl, I find a narrowly scoped task, which can be an algorithm or a data structure or any kind of small tasks that is small enough to be able to implement it in like 1 week, small enough to not spend too much time maintaining it, and I cut it out into a separate open source library that's generic purpose and can be used by other projects. And I make this library the world's fastest and simplest JavaScript library. And then I do it over and over and over again. And up to this point, I've been involved with over 100 projects. The ones in bold are those that I created and others that I either maintain or very actively contribute to. And to give you just some examples of the kind of stuff I work on, to render polygons with WebGL, you have to break it down into triangles. And it turns out that it's a pretty hard problem to break down a geometric polygon into triangles. So I made the world's simplest and fastest library to do that, and then ported it to C++. Then we needed to generate sprite sheets on the fly to create a texture for WebGL that would contain fonts and icons, etc. So I created a library that's very simple, very tiny, but it does this sprite sheet generation really efficiently. And then we needed to render third-party geographic data in our map, and I created a library called GeoJSON-VT that takes geographic data in GeoJSON format and processes it for rendering. And here you can see on this video 100 megabytes of data loaded directly in the browser, processed, and you can explore it seamlessly at 60 frames per second. We needed to make a clustering feature where nearby points are grouped together. And that's why I created a library called supercluster that does this, and does this very, very efficiently. And you can do some cool stuff with it, like this interactive heat map of 500,000 points, which wasn't really possible with previous generation mapping technologies. I'm also really fond of spatial indices, which is a special category of data structures that allow you to organize geometric data in a way that can be very efficiently searched. And I'm so fond of it that I made 6 different libraries for spatial indices. And one more example is that we have 2 parallel implementations of our mapping platform. One is JavaScript for the web, and another one C++ for native platforms like mobile. And to reconcile those 2 implementations so that they render the same thing, given the same data, I created a small, very simple library for very efficient comparison of screenshots for continuous testing. And apparently, according to GitHub, it's used by 53,000 repos, which was very surprising to me. So over the years, I've built this very unique experience of creating highly optimized, super fast JavaScript code. And there's one more cool example that I want to show you. So Mike Bostock is the author of a library called D3. It's now the industry standard for data visualization. I'm sure many of you have used it. And Mike created a new model for it called D3 Delaunay, which is for generating and manipulating the so-called Delaunay triangulations and Voronoi diagrams. And those are very important building blocks in data visualizations, and they're often used to create more powerful and interesting algorithms. So this module in D3 is a wrapper around a library that I created called Delaunator, which does all the heavy lifting of generating this triangulation really fast. And this is a great example of how ridiculous open source rivalry between different open source authors can get, because every open source author wants their library to be the fastest and best, and they compete with other authors, of course. So here's an example of triangulating 1 million points in JavaScript. 1 million points is quite a significant number for JavaScript. At least it was several years ago, but now JavaScript engines are really fast. So JavaScript can handle 1 million points. So in the beginning, there was a library that was called simply Delaunay. And this library triangulated 1 million points in 2 minutes and 30 seconds. And someone found it too slow for their purpose, so they created a new library that was called Delaunay Fast. And in hindsight, it probably wasn't a great idea to include the word fast in the library, but someone else tried to use this library and thought, hey, there's a name fast in this library, and it's not fast, it's too slow for my needs. And they created a new library. Can you guess what the name is? Faster Delaunay. And it was a huge improvement because it was 20 times faster than the previous library. And of course, this was too fun to pass for me. I wanted to take my own stab at it. And of course, I had absolutely no choice but to name this library the fastest Delaunay. But of course, I didn't, because I would eventually embarrass myself, because there are always people that are better, more talented, more skillful than me, and they will eventually create something that's faster and better. So I just named it Delaunator, and it's 5 times faster than the previous one. And also what's interesting about it is that someone else liked the implementation that I wrote and decided to port it to C++. And after all the necessary optimizations, the C++ implementation was only 10% faster than the JavaScript one. And I was also learning Rust. It's a very fascinating language. And I decided to port my library to Rust. And it was also only 10% faster. So it's a good example of how incredibly fast JavaScript can be if it's written very carefully. And you might think, looking at those weird algorithmic projects and complicated examples, that you need a strong mathematical computer science background in university for this. But that's not true, because when I studied in university, I never learned. This is an excerpt of a music video we made 15 years ago for my band. At that time, I was more concerned with drinking beer and playing Fallout and Baldur's Gate and Morrowind and doing other nerdy stuff. And I don't know how they teach algorithms in Catalan universities and other European universities, but in Ukrainian universities, the biggest problem in higher education is that they give you all kinds of extremely useful concepts and tools and completely fail to convey why you would ever need them in your life. So, of course, when you can't understand why you need it, you will never learn properly. So I didn't, and I was on the fourth year of my university, I got kicked out. So years later, I had to relearn everything from scratch because I needed it for my work. And I was no longer at the university. I had to do it on my own without all the academic flavor. And so I learned it in an unconventional, I would say, way. So I will now give you a super silly introduction to algorithms, Vladimir Agafonkin style. And I will start with the question of why. Why we need to learn this stuff. So imagine we face code that's really, really slow. And we have to do something about it. So there are three basic steps. First, we need to identify the exact bottleneck. What exactly is slow in our code? Then we need to find out why it's slow. And then we make it faster. And a disproportionate amount of attention goes to the first item in articles and tech talks. And it's profiling. So modern development tools are so amazing. It's just so incredibly easy and convenient to find what exactly is slow with your application. You find something is slow, you launch profiler, you drill down in your code, and you find an exact method that slows down your application. Or maybe you zoom into the slowest portion. And you see that this particular method, initialize style state, it spends 97% of the time. And now you need to understand why it's slow. And should it be slow? Maybe it does a lot of work because it needs to do a lot of work. Or maybe it could be faster. How do you know? So that's when we come to algorithms. Understanding why some code is slow and knowing how to make it faster, this is algorithmic thinking, because algorithms are about understanding the performance characteristics of your code. And the most important definition to make about slow code is that slow code is not bad code or code that somehow happens to be slow. Slow code is code that does unnecessary work, that does more work than needed for the goal. And our goal is to remove that unnecessary work. And I'll jump straight into some practical examples. There is a project called Rollup, which many of you perhaps used. It's an absolutely amazing, brilliant project for bundling JavaScript code. It generates highly efficient bundles, and as opposed to Webpack, that's tailored more towards applications, Rollup is very popular among open source library authors. For example, React and Babel use Rollup to generate their bundle. So I was debugging a particularly slow build of a complex project with Rollup, and the part that generated source maps was taking too long. So I started to dig deeper, and I came to these two lines of code that were particularly slow in Rollup. And Rollup uses a dependency called magic string for manipulating and generating source maps. And it's absolutely not obvious why these two lines of code would be slow. And source maps have this string form that looks like this. So to understand why this is slow, you have to dig into this magic string dependency and see what's going on there. So I'm looking at magic string. It does some magic with source maps, generates a JavaScript object that represents the source map, and then it encodes this into this special string form. And then Rollup receives this string, decodes it into a JavaScript object for further manipulation. For example, for merging source maps of different files into one source map. And now, can you see what's wrong with this code? These two lines are completely useless. They're not needed, because you take an object representing a source map, convert it to a string, and immediately convert it back. No one needs that. So if you remove those two lines, it will just magically get better and faster. So the problem is that these two lines of code are completely in a separate projects even, not even in separate functions or separate files, in separate projects. So it's not obvious that this happens until you understand what each dependency does. When you're thinking about performance, there's your code and there's this huge amount of dependencies that you use. And to understand a performance problem, you'll have to dig deeper into dependencies to understand what's going on. Because very often, someone will think, when an application is slow, they will think, oh, damn, why did I use Angular? If I used React, it would be blazing fast. And then they write an application in React, and it's still slow. What gives? So if you don't understand what happens under the hood, you will not understand the performance problem. So I made a separate method that returns a JavaScript object rather than a string, and we could just remove those two lines. And source map generation in Rollup got 40% better. Now to explain more difficult concepts in algorithms performance, I have to introduce a new concept of algorithmic complexity. You may have seen those notations, and I guess most of you even know what they mean. But let's just assume that you don't know everything, and I will introduce them from scratch to you. Algorithmic complexity is a way to describe how performance scales with input size, which is critical for understanding why code is slow and how to make it faster. So we have O1, which is a constant operation. Constant complexity means that no matter how many items we have, we'll just need one operation to do this. On, or linear complexity, for 1,000 items, we will need approximately 1,000 operations, which is much worse, of course. Then there is On squared, so-called quadratic complexity. And for 1,000 items, this will be 1 million operations, which is kind of difficult in JavaScript. N cubed will be 1 billion, and in most browsers, even the most modern ones, they will just freeze with that kind of amount. And let's dig deeper. Constant complexity. This is a complexity that you don't have to worry about, usually. It usually means that it's instant and it's not a bottleneck. So you have to look elsewhere. Oh, and linear complexity. You can identify it everywhere you have a loop, for example. And linear complexity is suspicious. And suspicious it is because it's really easy for it to turn into higher order complexities without you noticing. So then there's quadratic complexity. And quadratic complexity is terribly, unacceptably slow. Every time you see two loops that are nested, that means that your code can be somehow optimized, usually. And this may be very obvious when you look at this kind of code where you clearly see two nested loops. But imagine this example where you have one loop and you think it's linear, but then you find that there's an index of call. And index of, what it does under the hood is that it has to go through all the elements to check which one has the index we need. So it's also linear, and combined they generate quadratic complexity. And it may still be obvious, but what if those two operations are in different methods? And what if they're in different files or different projects even? This is a very, very easy mistake to make. It's so easy that, in fact, there's a separate Tumblr blog about this called Accidentally Quadratic. That's specifically about quadratic complexity problems discovered in very major established projects, like, for example, Elasticsearch or Chrome browser or React or whatever. And of course, there's a cubic complexity. And that usually means that you have to throw your code away and start again. So in summary, instant complexity, linear complexity, suspicious, quadratic, terribly slow, and cubic throwout. Let's look at an example. D3AA, the library that I mentioned earlier, it was slower than I'd like, and I started looking into ways of optimizing that. And I came upon this part of code that was particularly slow. And you don't have to understand what's going on in this code now. Here's the point, how I looked at this code. I'm looking at it, and hey, I see a loop. That's already suspicious. I need to look further. Then I see a second loop inside. Oh, that's bad. That means it's quadratic. That's already terribly slow and needs to be optimized. And then I look further, and I see a splice inside, which is also a linear operation. So it's a cubic complexity overall. And what do you need to do? Of course, you need to throw it out and write from scratch. So I rewrote this part of code, and it made the library overall about 3 times faster. So it's very easy to fall into a trap because many native browser methods are linear complexity, and you don't often realize things like index of, splice, includes, find, sum, reduce, etc. They have to go over all the items, or most of the items. So you have to be really careful when you use them. And so far I talked about computational complexity, but there's also a whole different aspect to performance, which is memory complexity. And in terms of avoiding unnecessary work, optimizing memory complexity means making sure that we don't allocate more memory than we actually need for our program. And it's also really easy to fall into a trap here because many native browser methods allocate a lot of new memory. Things like slice, which copy the array in whole, concat, map, filter, split. And it's very popular today to write in this so-called functional style. And it's even preferable in many cases because the code is concise, it's expressive. But if this code is in a very critically hot performance path, So let's take a closer look at what's happening. We copy the array once and allocate some space for it. Then we concat it with some other array, and we allocate another whole array for it. Then we map it and allocate one more array for it. And then we filter and generate one more array for it. And we allocate memory and throw it out immediately 4 times. And that's the epitome of unnecessary work. And it might not be noticeable, but if it's in critical code paths, it may be noticeable. And rewriting it with like traditional for loops may improve performance. So I'm often skeptical about all those new approaches because all I think about is how much memory it allocates. Then there's this really simple case of a function returning multiple values. We return them in an array, and then we immediately destructure the result into separate values. So we created a new array object, and then we discarded it immediately because we don't need it. And that's also unnecessary work. If it's on the hot, critical performance path, you would have to inline this function. Another practical example, and I forgot to mention that every practical example, at the top you can see the exact GitHub URL of a pull request that I made to do this optimization. So when you watch slides afterwards, you can go and look at GitHub at the exact changes that I made. So source map codec is another dependency of rollup that does this encoding and decoding of source maps from string to an object and backwards. Particularly decoding string into an object was slow, and this is what it essentially did. It took a string, split it into lines, then for each line it split into segments. Each segment it decoded into an array of numbers, and then it did something with that array. At every point, at every iteration, it generated new arrays that it discarded afterwards. So instead, I decided to rewrite this whole approach from scratch, and instead I made one loop that goes over each character of a string separately and does not allocate memory at all. So we don't need any allocations. We just go character by character and decode it, and it was 3 times faster. And I didn't mention a whole new, very important category of algorithmic complexity, which is logarithmic complexity. What many people don't understand about logarithmic complexity is how amazing it is. So we have this range from constant complexity to linear one. Where do you think logarithmic lies? Somewhere in the middle, maybe? It's actually somewhere there. It's amazingly fast. And if we look at a million items example, logarithmic complexity will be just 20 operations instead of million. That's a huge difference. And the most popular logarithmic algorithm is binary search. And once you understand what it does, you start to notice applications for it everywhere. It just clicks, and then you can apply it and make things faster. And binary search is really simple, actually. If you have a sorted array of items and you need to find a particular item, you look at the middle. And if our item is somewhere to the left or to the right, we just discard half of the items and look further. And take middle again. And again, and again, and that way we find our element really quickly. We just discard half of the elements on each iteration. And that's what I did in this pull request, which was, again, about source maps, because I really like them, apparently. There were some really fringe cases where a bundle of rollup would take minutes. And I tried to discover what's wrong there, and turned out that there were cases that there was one already minified line of code turned into a source map, and we searched for particular segments on this line with a simple loop. This is the whole change that I made. We wrote it to use binary search, and it got 40 times faster for that particular case. So algorithmic optimization is trying to reduce the complexity for linear to logarithmic, from n log n to linear, etc. And of course, cubic you just throw out. And an easy model to show, to understand how to do that, how to reduce complexity, is imagine we have multiple operations that are really slow, and they're done repeatedly. What do we do to make them faster? You organize data in some way. You shuffle it somehow, maybe sort it, maybe put it in some data structures, and put it in a way that these operations are much faster. And it becomes like this. So algorithmic optimization is doing more at the beginning to do less every next time. And that's what indexing is about, for example. There are plenty of data structures that you can learn and use. And of course, I will not go over them. But I have a favorite data structure. Can you guess what that one is? Sorted array. It's a data structure because it's an organization of items in a certain way that allows very efficient search in many cases. There are a lot of very cool algorithms related to sorting. For example, if you have 1 million points, 1 million items, and you need to take the top 50, you can do that in linear time without sorting the whole array with a special algorithm called selection. And of course, I wrote a separate library for it. Then there's this library called KDBush, which is for indexing geometric points, which allows really fast search of points. For example, you have millions of points and you want to see in a particular area what points are there, or 10 closest points to this point. How do you do that? KDBush, a library that I wrote, it's nothing more than a fancily sorted array. We take all this data and we sort it in a way that all points that are on the left go first and those that are on the right go second. Then we sort every half again, but those that are on the left are all at the top and the others at the bottom. And we alternate those partitions until we have this fancily sorted array that can be extremely quickly searched. And also, one of my favorite data structures is priority tree, which I like so much that I made 2 libraries for it. There are various data structures that you can use in JavaScript, but sometimes it helps to know what data structures are used in the JavaScript engine itself. Here's an example of an object with keys 1, 2, 3. And there's another example. It's the same, but the keys are 0, 1, 2. What's the difference? You would think that JavaScript represents them in the same way. But actually, this one is a hash table because it thinks it's an object with arbitrary string keys. And this one is not much different from an array because it's equivalent to simple array, 10, 20, 30. So there was a library called Istanbul for instrumenting code and generating code coverage. It evolved into a project which is very popular now called NIC, New York. And this instrumentation was really slow for our project. It was a huge project, and generating instrumentation was many, many times slower than running tests on its own. So I started digging deeper into it, and it's a really, really popular tool that's used very extensively. And it turned out that if you take this, the object where the statistics about which lines are called how many times, If you take it and change one line of code so that it starts with 0, it gets 15 times faster. And this is a very popular established project. So people make mistakes all the time. Even really popular projects have a lot of unoptimal code. And people take established code for granted and afraid to contribute and change something, because they think that smarter and better engineers already took care of it, but that's not true. You can always contribute. You can always find something to improve. So established doesn't mean best, and there is always room for improvement. So my last slide, a set of tips. Learn how things work under the hood. Don't hesitate to dig inside frameworks. Contribute to open source is a great way to learn. Don't be afraid to reinvent the wheel, because don't reinvent the wheel is one of the stupidest advices I've ever heard. Please reinvent the wheel, create new stuff, learn, and make the world better. Simplify your code, because simpler code is easier to understand and easier to optimize. And if you practice optimization, you'll learn eventually to write fast code intuitively from the start. Thank you.